Welcome once again to some physics lectures. This is chapter 5, all about relativity. Actually, really just about the theory of special relativity. General relativity, I'm not really going to touch on. At this point, the course is getting into what we call modern physics. Modern meaning in the past 100 years or so at this point. In the early 1900s, there were two paradigm-shifting theories that were developed. And at this point we call one the theory of relativity, the other is quantum theory. So we'll get to quantum theory a little bit later. Today we're going to talk about the theory of relativity. So there are plenty of ways that relativity plays into our modern day life. One of the most often pointed to examples is with GPS satellites. GPS is a system that uses very precise clocks in order to pinpoint locations on the Earth's surface. So precise, in fact, that you get to the point of measuring time periods that actually vary noticeably due just to the difference in motion of the satellites and the Earth. Also, there's effects due to general relativity, gravitational fields. Both of those things due to relativity, broadly speaking. So something to point out and keep in mind while we're talking about these things in modern physics is that in the past, all the stuff we talked about is basically what you would classify as now classical physics, and it deals with some pretty strange stuff at times, but for the most part, it can be related to our sort of day-to-day or normal life, like thermodynamics, heat, and electricity. You get shocked, and motion. You know, you're throwing balls, right? All that stuff we deal with in sort of our normal life. Modern physics deals with a lot of stuff that is very different from what we normally deal with. In relativity, we're talking about special relativity. In particular, we're talking about things that are moving incredibly fast, like unimaginably fast, almost. Large portions of the speed of light, close to the speed of light. Some very odd things that actually happen when you do have objects that move close to the speed of light is two of the main things that come out are this thing called time dilation. So a clock that moves by you very, very fast, you're going to see it as ticking a little bit slower, meaning that the time periods are elongated in that moving clock. They're dilated, in a sense. The other thing is length contraction, where an object that zooms by really fast actually contracts a little bit. It looks shorter in the direction that it's moving relative to you. We don't really see this stuff normally, and that's because we don't normally deal with objects on our scale that are moving that fast. And, you know, it's hard to maybe internalize some of this information because it seems so different from your normal experience. But there are like analogies, you know, that might help where it's sort of like a different scale of things. The way that things act is very different. I tried to think of some good analogies. A couple I came up with were like, if you're intending to build like a sandcastle on the beach, that's one way. There's going to be some stuff you got to do, and it's pretty straightforward, pretty easy. Versus you're trying to build a skyscraper, this is a hugely different scale, and the things that go on in order to actually build that are hugely different. Other things you might think of is like the general way you think of a pebble acting. You can pick it up, I can toss it up and down, that kind of stuff. Versus the way that the moon acts. They're both rocks in a sense, but they act incredibly differently because they're incredibly different scales. And the last one I thought of is like, if you're financing something, right? Imagine you're financing a candy bar. Not very difficult. You can raise some money to finance a candy bar pretty easily. Versus financing a satellite or the International Space Station, right? Vastly different things are going to be needed. And the way things are going to act is going to be quite different in those different situations. We're actually used to things being very different when they're in different situations. A very important concept when talking about relativity, the name itself is talking about relative frames of reference, right? A relative position, relative motion. This concept of a frame of reference or a reference frame, both mean the same thing, is something that we're going to need, and you can understand this concept pretty well. This is a nice little GIF showing the two different frames of reference, maybe for like a car driving down the street. So the car starts on one end of the block accelerates and then slows down and stops at the other end of the block. From the maps frame, or maybe the Earth's frame, right? If you're just standing on the Earth and watching this car, you see the car speed up and then constant for a second, slow down and stop. But from the car's frame of reference, it's actually the world that's moving by it. The world starts to just accelerate one backwards and then slow down, decelerate a bit until it stops moving again. So all that is to say that motion in general is relative to your frame of reference. This is actually an example of what you would call a non-inertial reference frame because it involves objects that are accelerating. However, in special relativity, we only deal with inertial reference frames. And that's dealing with objects or frames of reference that are moving at constant velocities relative to each other. So instead of this car accelerating and slowing down, you might think of just a car that you watch speeding by at 60 miles an hour, right? Constant speed going by. You've already had to think about two different reference frames back in mechanics when you're thinking about the position of objects, right? And sort of looking at it, well, the position from a person standing on the Earth maybe versus a position or the frame of reference of a person in a moving car or some kind of moving vehicle. And in classical physics, you get what's known as, or we use what's known as Galilean relativity. So if you have two frames of reference, right, the black and then the blue frame, and the blue frame, we put these little primes on the X, Y, and Z to indicate this is what we call the primed frame. It's another frame of reference, which is moving relative to the unprimed one, the black axes here. And it's indicated that it's moving in the positive x direction with a speed v. So for classical physics, we end up getting these transformations for the position of objects in the rest frame versus the moving frame. So the rest frame is the unprimed, the moving frame is the primed frame. Pretty straightforward. Only the x position is affected because there's movement in the x direction. This is assuming that at time 0, these two frames are overlapping, right? So the x positions are the same at t equals 0. And then for velocity transformations, very similar to all you're doing to get, say, the velocity in one frame versus another frame. As long as you're just moving the x direction, you simply add that speed of the motion in the x direction. This is a pretty intuitive thing. You know, if you see somebody throwing a ball while they're on a train, then you pretty well understand that the motion you're going to see of the ball is the motion from the velocity of the person throwing it and the velocity of the train, right? So you're going to see that ball going as fast as the train plus the speed they threw it. These are how things normally act, right, in our normal day-to-day sort of experience. So relativity actually tells us that this is just our experience because this is how things act when speeds are much less than the speed of light, the speeds we're talking about in these reference frames. When we talk about things that actually are moving then close to the speed of light or near the speed of light, we get different transformations. These are the Galilean transformations for position and velocity. We're going to end up getting what's known as the Lorentzian transformations, or Lorentz transformations. It's going to be an important thing that whatever we get for our theory of relativity, we can still reduce it back down to what we know works in our normal day-to-day life. So these Galilean transformations, we should be able to get back to these when the speeds we're talking about are actually much less than the speed of light. This is what's known as continuity. If you have a theory and it predicts things at these very different scales, these very different sort of situations, you need that theory to still agree with what's known to work in the normal situation. As I mentioned, all we're going to be dealing with in this chapter is actually the theory of special relativity. Special meaning we're only talking about constant velocities and inertial reference frames. The theory of special relativity essentially is two postulates and the consequences of those postulates. So it was Einstein that proposed these back in the early 1900s. The first postulate is saying that the laws of physics are the same in all inertial reference frames. This is known as the invariance of physical laws. Here we have pictures of two reference frames, right, that are basically inertial. One is standing on the Earth, watching this car zoom by. Right? You're standing here at rest, the car is zooming by at a constant speed. The opposite of that, or the inverse of that, is you're in the car and you're watching somebody on the Earth and they're actually speeding by in the opposite direction. Right? But it's the same picture just from the two different reference frames. And the relative velocity is the same regardless of which frame of reference you're in. It's just one's going in the positive direction, one's going in the negative direction. So another way of saying this first postulate is that there's no preferred reference frame. The universe doesn't have any preferred reference frame, and there's no absolute reference points in the universe either. The book actually goes into a little bit more of the history that I'm going to tell you about, but it was thought that the electromagnetic waves that came out of Maxwell's equations needed a medium to propagate through. So just like water waves need water, sound waves need some kind of air usually, or gas, or water too, right? But they need a medium, they need something to travel through. So it was thought that the electromagnetic waves also need a medium, which I think they called the ether. Cool name, right? And basically, in trying to detect the ether, to try to show that it was a thing, and to try to see the motion of the Earth in the ether, Michelson actually, from what we know about the interferometer, he and this guy Morey, I think, developed an experiment with interferometers to try to measure the motion of the Earth through this ether. Basically, they couldn't detect any motion relative to some ether. So they kind of, in a way, showed that there wasn't really an ether, and then also in the process, they ended up essentially showing that the speed of light was the same regardless of which reference frame you're in. Like if you were in a speeding reference frame relative to a stationary reference frame, it looked like the speed of light was just the speed of light. It didn't add up like the Galilean velocity transformations, right? So if you look at Maxwell's equations, there's nothing pointing to any reference frames there. In free space, you just get out this wave equation, and that wave has a speed c. So Einstein basically took this to heart and came up with the second postulate of special relativity, that light travels in a vacuum with the same speed c regardless of which reference frame you're in all reference frames. I should note that, right, c is the speed of light in a vacuum. We know that light actually travels different speeds in mediums, and that's because it's interacting with the atoms and molecules in that medium. That's what ends up giving us this property of refraction. But that doesn't have to do with different reference frames. That has to do with light interacting with the materials there. We're just going to think about light in a vacuum. We're not going to worry about it interacting with atoms and molecules. So it's going to travel at c. Like I said, just those two postulates, it turns out, have some very startling consequences. The first we're going to think about is what's known as simultaneity, or the property of events being simultaneous, or coming before, coming after. So imagine if you have two events, like A and B, A could happen first, then B. A and B could happen at the same time, or B could happen first and then A. So these are time intervals, essentially. These are events that punctuate the time intervals. How much time happens, right? If it's some time, then A is before B. If there's no time between the intervals, then they're simultaneous. If the interval is negative, maybe, then B happened before A. This idea of simultaneity ends up boiling down to talking about time intervals of time. And when we're thinking about intervals of time, we're going to think a lot about light moving. So thinking about flashes of light and when somebody sees those flashes of light, or light bouncing around, good to that too. So if you think about two events, say like a person sitting on a train here, and there's a light on the front of the train, there's a light on the back of the train, and those lights are going to just flash real quick. Right? There's this front flash and the back flash. Depending on your frame of reference, you're going to say maybe that the front flash happened before the back one, or they happened at the same time, or the back was first and the front was second. It turns out that the idea of things happening simultaneously is actually dependent on your frame of reference. So let's see how that might change. Okay, so we have that person sitting in the train, right? There's the front flash, there's the back flash, and now the train is going to be zooming along very, very fast, right? Because if we want to talk about relativistic effects, it's got to be moving at a decent fraction of the speed of light. So this is not a normal train. This is a very, very fast moving train. So you have that person on the train. Those things are going to flash. You also have now an observer, observer B, who's outside the train and watching the train zoom by. So what happens, right? Think about the situation, and right as the two observers are overlapping, right, A and B are overlapping, the front and the back let off their flashes. Right? But we know that, light is a wave. It takes a certain amount of time to propagate at a certain speed, c. So if we propagate those waves, they're going to just keep getting closer to each other, and then we get to picture B, where they're now closer together, but the observer A has actually advanced forward in that time, And so now that wave is going to actually hit observer A. So observer A is going to say, oh, the front flash went up. You keep advancing those wavefronts a little bit more. Eventually, those two wavefronts are going to overlap right at B. Observer B is going to say then, those flashes happened at the same time. They're simultaneous. But observer A saw the front flash first, and it's not even until after all this happens that the back flash is going to keep propagating and eventually make it to observer A. So observer A says front, then back. Observer B says same time, simultaneous. So they don't agree on the order of the events, and the very strange thing is that they're both right. These are both valid observations of these events. Simultaneity, the ordering of events, turns out to be relative to your frame of reference. It's probably important to point out that this fact has been tested rigorously many times since it was proposed, and it's always been proven true, or it's never failed any of these tests. Again, it seems like a very odd thing to say that the ordering of events and time intervals are going to be disagreed upon, but remember, that's your intuition telling you that, right? Because we deal with normal events. We deal with things not going very fast. Well, very fast relative to the speed of light. Here, talking about something very different. This train is going half the speed of light, say. We shouldn't expect that our intuition is going to be correct here. Part of the point of doing science, is to develop new intuition. So we're talking about ordering of events. Remember, it comes down to measuring time intervals. The most fundamental way of measuring time intervals turns out to be using what we call like a light clock, right? Using the motion of light waves, or you can imagine them just as photons, right? Like photons bouncing around. So this GIF is showing a theoretical or very simple idea of what a light clock might be, which is you just have parallel mirrors and somehow have a photon inside of there just bouncing back and forth. It's going to keep reflecting back and forth, back and forth, back and forth. And one round trip, we can imagine as a tick of that clock. Right? So it goes up, down, tick, up, down, tick. Okay, so if that light clock, that's our clock, that's how we're going to tick off time, then let's think about what it looks like if you observe a light clock from two different reference frames. Right? One that's moving very fast relative to the other. In this picture here, we have one reference frame of, say, an astronaut who's in space shuttle orbiting Earth, and so they're essentially just moving by very, very fast relative to somebody standing on the Earth, an observer on the Earth here, watching that space shuttle go by, watching that light clock go by. Okay, so let's think about a tick in each of these reference frames, right? In reference frame A, the astronaut is at rest relative to the clock, so he just sees the photon go up and go down. So the distance that photon is traveling is just 2d, that height of the clock. So that should be equal to the speed that the photon is traveling, c, multiplied by, we're going to call delta tau. So the book often uses tau as the time measured in the, well, at rest relative to the light clock. So the astronaut's at rest in the same reference frame as the light clock, so he gets the tau here. In B though, right, in B the observer on the Earth is actually watching the photon go along this diagonal path, because that shuttle is moving along. The reference frame is in motion here. So the photon actually goes up along here, bounces, and comes back down. So it's traveling on this S and then another length S. So it's actually 2s, the distance that this photon travels. And you can use some simple geometry in order to write that in terms of the distance that this shuttle has traveled and the height of the clock. That's going to turn out to be 2s is 2 times the square root of d squared plus l squared, which should be equal to the speed that the photon is traveling multiplied by regular t. So regular t here is the time interval that the observer is seeing the clock tick. Right? That's one clock in this reference frame that's watching this other reference frame zoom by. And it's very important actually that in both of these reference frames, we've taken the second postulate here to say that both of these reference frames see the photon traveling at this speed c. So we also want to relate L to the relative velocity of these reference frames and the time that the observer on the Earth is watching, right? So the observer on the Earth is seeing this tick happen while that reference frame that's moving at the speed v. So L is actually 1/2 of the distance that that shuttle traveled in delta t. So yeah, so L, I'm going to say is this. Right. Let's now try to relate delta tau, the time in the reference frame at rest of the clock, to delta t, the time observed from the person watching the clock zoom by. So taking that 2s and now plugging in what we know L is, how that's related. Get that. And if we divide by that 2 and then square both sides, we're going to get that. And then subtracting this term and then square rooting both sides. We're going to get to there, right? And now I'm trying to eventually relate it back to this other time interval, the delta tau here. So let's just do this. If this was d, then I can just multiply both sides by d, right? 2d, 2d, so this should actually be equal to that c delta tau. Oh, it looks like I forgot this square. Right? That was actually a squared term. My bad. And that means that there's actually this delta t in both of these terms. So I can factor it out, and it's just going to become, the square root's going to take away that extra square. And let's see, there's, should also be a 1/2 in both these terms. And also somehow put that on the outside. So I can actually factor out this 1/2 and delta t, which is going to leave me with just a c squared minus b squared on the inside of this square root. And then these 2's are going to cancel. And then what we're going to do is actually factor out this c squared, factor out a c squared from both of these. So this one's going to end up being b squared over c squared. And when I factor the c squared out of the square root, it loses that square. So we're going to end up just with this. And then finally, right, this was still equal to c delta tau. So those c's cancel, and there we go. We have delta tau, the time interval measured in the frame at rest with respect to the moving frame, is equal to this factor multiplied by the time interval that's watching the moving frame go by. So usually, well, I'm going to just reorder this so that now we're talking about the time interval in the reference frame watching the clock move versus that time interval in the clock, and it's related, proportional by this factor. So this is something that's going to come up very often in relativity, special relativity. It's known as the Lorentz factor. We usually just write it as gamma. And that's where it comes from. And there you have it. This is how the two time intervals, right, one in a frame of reference that's at rest with respect to the light clock, that's delta tau, and one in a frame that's watching that light clock zoom by at a speed v. that time interval that you measure in the reference frame of the light clock is what's known as the proper time. One definition of the proper time is the time measured in the reference frame of the two events, right? The events are the photon leaves the mirror, goes up, comes back down, right? Left, come back down. That's a tick. Two events left, hitting it. Or another way of saying that is the measurements that are made at rest relative to these events. Yeah, so the book is a little bit, I don't know, maybe sloppy here. Sometimes they'll write the proper time as tau, sometimes they'll write it as t naught. Sometimes we'll even just write t, and then the moving reference frame is t prime. But regardless, there it is. So let's think a little bit more about this Lorentz factor. So this is a graph of the Lorentz factor where you're graphing gamma, the Lorentz factor, versus the velocity, the relative velocity of the two frames, right? How fast one frame is going relative to this other one. And, well, that's the form of the Lorentz factor. So when you plot it, it's an asymptote, right? It asymptotes at c. So some other things to note is when the velocity is relatively low compared to the speed of light, gamma is 1, right? Gamma is very, very close to 1, essentially 1 for most speeds that we normally deal with. Once you start getting to speeds that are like 10% the speed of light, then this gamma starts becoming a bit different from 1, right? Enough that it can start to factor into things. I might be a little sloppy, sometimes I'll call it the gamma factor. I'm not even sure why that's a thing, but it is the letter gamma, but it's the Lorentz factor. Yeah, so actually roughly 10% the speed of light is somewhat like a boundary almost, where you might say that that's where these relativistic effects start to really play in. You really have to start taking that into account. But 10% the speed of light is still incredibly fast, right? That's 3 times 10 to the 7th meters per second. Or in miles per hour, it's something like 70 million miles per hour. Right? Incredibly fast still. Oh yeah, and just to note then, that when the velocity is very small, right, the Lorentz factor is essentially equal to 1. As the velocity approaches the speed of light, the Lorentz factor approaches infinity. Right? That's the asymptote there. Yeah, and if you look back at the proper time and the moving reference frame time, the proper time is the shortest amount of time you would measure these two events, the time interval between these two events. The moving reference frame is always going to be longer time intervals. And that's just because gamma is just either equal to 1 or going towards infinity. It's never less than 1. All right, so let's try out an example of thinking about this hypersonic vehicle, very, very fast, right? But we'll see, only very, very fast for normal situations. So it's going 21,000 kilometers per hour or 5,830 meters per second. So we want to say what is the difference essentially between a clock that's ticking in that vehicle versus a clock that's sitting on the Earth and watching that vehicle zoom by. So there's a clock in the hypersonic vehicle, meaning that the clock is ticking, that's the proper time of that clock, is 1 second, right? We're going to say, where the question says, the clock in the vehicle ticks for 1 second, what does an observer on the Earth see that or measure as that time interval? So that's the proper time, and the relative velocity of these frames is that 5,830 meters per second. So what we're going to do is just calculate this Lorentz factor. Do that first and then apply it to the time interval. Notice that the Lorentz factor has no units. Turns out this is, oh man, I think that's about right. Very, 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 very small. 1 plus 1.89 times 10 to the minus 10. Right? Almost 1. For most intents and purposes, it's 1. Okay? Meaning that the time interval that you're going to measure on Earth, right, it was just gamma times the proper time, and the proper time was 1 second, so it's just this times the 1 second. So essentially now we just have units to this number. Very similar to 1 second, almost the same as 1 second for any normal purposes. So like I said, very fast relative to normal situations. Not very fast relative to the speed of light. All right, how about another example having to do with proper times and times in moving reference frames. In this example, they're talking about a muon, which is a fundamental particle, essentially a big fat electron. And they can be produced in the upper atmosphere when stuff from outer space collides with the upper atmosphere. Sometimes, or oftentimes actually, you get muons that are produced there and they start to zoom down towards the Earth's surface. So imagine a muon was created up at this top of the atmosphere here and it's going to zoom down to the Earth's surface. The muon is going to be traveling at a constant velocity. It lives for 2.2 microseconds as measured in its own reference frame. So that's like watching a clock on the muon's hypothetical arm. It's 2.2 microseconds. And if it's traveling relative to the Earth's surface, 0.95 c, or 95% the speed of light, then how long would a person on the Earth's surface say that that muon took to get from up there down here? So let's go back to this formula. Bad. Maybe I didn't actually even say this before. This is the formula for time dilation, right? So this is the time in the stationary clock's reference frame, and it's going to be multiplied by this factor that's 1 or greater than 1, right? So this is the time dilating and elongating in terms of the reference frame that's moving relative to the stationary clock there, or the stationary reference frame. Cool, so what is the gamma factor when, yeah, I said it again, what's the Lorentz factor when the velocity, or the relative velocity of these frames is 95% the speed of light? Oops. I'm going to get that. And it turns out these c's are going to cancel each other out here. 1 over 1 minus 0.95, or square root of 0.05. Turns out this is 3.2. We're going to keep a few decimal places here. Oh, 3.2. That's the Lorentz factor, right? So the time that the earthbound person is going to measure for the, well, how long it took this muon to travel, it's going to be that, okay? Which turns out to be, let's see, a little over 7 microseconds, right? Because that Lorentz factor is a little over 3, so a little over 3 times the time, the lifetime that the muon experiences itself. So here it wasn't exactly as important that I kept more decimal places, but in general, when you're doing calculations with gamma, it's a good idea to keep a good number of decimal places. I said gamma again, Lorentz factor. So another way of putting that, the results of that, is that the earthbound observer actually measures the muon lasting for a longer time than the muon itself sees. So this has some important experimental implications in that if there wasn't relativity, then muons generally wouldn't actually even make it to the Earth's surface. But because there is this time dilation that happens, muons do actually, a lot of them make it to the Earth's surface. In this image, actually, we see hints at what we're going to look at next is length contraction. So the muon actually sees a shorter length that it's traveling through versus the stationary frame relative to Earth. The fact that time intervals are different now means lengths are going to contract in different reference frames. Thinking back to that train moving along, an observer on the train, an observer at the station, say, or on the Earth just watching the train go by, if you want to measure the length of that train, the way you could probably have to do it or a very fundamental way of doing it, is you essentially have a light that's going to flash when the front of the train is moving out of the station, and then flash again when the back of the train passes out of the station. Right? So you have this train coming by very, 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 very fast, right? Right when the front hits that end of the station, light flash. Right when the back hits that station, light flash. Right? And the time that you measure is going to be different if you're on the standing on the station, on the platform, or if you're on the train. And if you take the length of the train to just be the velocity of the train multiplied by the time that it took the train to pass the station, the consequence of that is that those two observers are going to say that the train had a different length. And it's pretty straightforward to show that that length is going to contract. It's going to contract by this factor, the Lorentz factor, gamma here. So L0 is what's called the proper length. And just like the proper time, it's the length that's measured in a reference frame stationary to the object. So the picture here is showing like a little ruler. And if you're in the reference frame of the ruler, you're measuring the proper length of that ruler. You're at rest relative to the ruler, so you're going to see its proper length. Versus if you watch that ruler zoom by very, very fast, you're not seeing its proper length, you're seeing its contracted length. You're in a different reference frame from the ruler. And something maybe to point out is that when the velocity that we're talking about, or the relative motion here, when that velocity is really small compared to the speed of light, then that v squared over c squared basically becomes 0, and you're just multiplying by 1. So that is to say that when you're not moving at anywhere near relativistic speeds, the length in both frames is the same. And so that's how we get back to our sort of normal look at the world. So then when v is going towards the speed of light, you're getting to very relativistic speeds. This factor is becoming 1 minus 1, and you're multiplying the proper length by a number going towards 0, so the length that you see of something goes towards 0. This is a contraction, right? That's the length contraction. But again, only really comes into play when you're talking about speeds that are a decent fraction of the speed of light. Okay, so let's look at this example. We got this astronaut who's going to be traveling in the spacecraft very fast to the nearest star, Alpha Centauri, and they're traveling so fast, in fact, that the Lorentz factor is going to be 30. So this is the Lorentz factor for somebody sitting on Earth versus the moving reference frame that is the astronaut zooming along. Alpha Centauri is 4.3 light years away, as measured by the Earth observer. How far apart is Earth and Alpha Centauri as measured by the astronaut? So the proper length is the length measured in the frame where the Earth and the Alpha Centauri are essentially stationary relative to each other. That's the Earth's reference frame here. So that's going to be that 4.3 light years. And they told us the gamma factor, the Lorentz factor, is 30. So for A, the length measured by the person in the spacecraft that's moving relative to that distance, that moving relative to Earth and Alpha Centauri, is going to be proper length over gamma, 4.3 light years over 30. .14-ish light years, right? Much shorter length that they're going to see. And then in B, we're asked in terms of C, what is the astronaut's velocity relative to Earth? You can neglect the motion of the Earth relative to the Sun. Okay, so assuming Earth is just sitting here stationary, Alpha Centauri is sitting here stationary, what is the velocity that's going to give us that gamma factor? Well, remember gamma was, keep saying gamma, the Lorentz factor. It's that. So if we square both of these things and then invert them, we get that. And we're trying to figure out what this velocity is, so let's subtract it over, and then subtract this 1 over gamma squared. Multiply by C, and square root everything.
this should be squared. Okay. Or maybe we just write it as c outside of here. Because we're looking at it, they say, in relative to the speed of light, so we're just leaving c as c. Turns out that this stuff here is 0.99944 c. So that's all this stuff, right? That's the fraction of the speed of light that we're talking about. It's 99.944% the speed of light. In order to get a Lorentz factor that large, you got to be going very, very, very fast, pretty close to the speed of light. So also to note here that this fact that length contracts in the direction of motion, when you're talking about, well, you only really see this effect when something's going very, very fast, has also been confirmed experimentally numerous times in a multitude of ways. One of those ways is when we were talking about the electric field created from a moving electron. In things like particle accelerators, where you have bunches of electrons and you're just zooming them around, you're accelerating, again, going incredibly fast, you can measure the electric field created by these electrons, and it only really makes sense if the length that the electron is seeing is contracted. So it essentially ends up squeezing this electric field that the observer watching the electron zoom by is going to see. This length contraction, also going back to the muon example, allows us to understand why the muon actually reaches the Earth's surface. It's because the length that it is seeing is much shorter than the distance from the top of the atmosphere to the surface that we see, right? It sees this contracted length in its reference frame.